A great pleasure for me to introduce Gil-Fuster. That is currently, I guess, last year PhD student at Freie Universität in Berlin, in the group by Jens Heisert. And I think that he's also collaborating in the group of Vedran Junko in Leiden. And he is a great expert on various topics in quantum machine learning, various aspects, formal aspects. I think that the seminar of today will be about this. So, stage yours.
Thank you for the kind invitation and for the kind introduction. Just as a disclaimer, I don't see you on the screen. So if anyone wants to say something, feel free to unmute yourself, because even if you move around, I will not be able to see it. Cool. Yeah, I'm Elies. I'm a PhD student here in Berlin, and indeed, I work very closely with the team in Leiden, led by Vedran. Today, yeah, as you mentioned, I work on some of the formal aspects of quantum machine learning, so like quantum machine learning theory, and I'll be talking about from the very pedantic point of view, what is the current status in terms of how excited we should be about quantum advantage in learning tasks using quantum machine learning models of the type we all like. Yeah, as I said, feel free to interrupt me at any point. And okay, because if we're all here, we have heard about the fact that quantum computers should be more powerful than classical computers for some specific tasks. And this is very well formalized in the framework of quantum advantage in computation. There are computations that classical computers cannot perform efficiently, or we don't believe that they can perform efficiently, whereas quantum computers can perform them efficiently. And one would expect that because there are things we can compute more efficiently, then there should also be things that we can learn more efficiently. And so I'll be making a distinction between quantum advantage in computation versus quantum advantage in learning. And this gut feeling is the starting point of quantum machine learning and quantum learning theory. And indeed, there are kind of very generic recipes for how you can turn computational advantages into learning advantages. Particularly some early examples and more newer ones that kind of make intuitive sense come from either cryptography or from some corners of condensed matter physics, where there are some functions that classical computers cannot compute efficiently. Then abstractly, you could convince yourself that you could define some learning task that could be a bit strange, but such that the only acceptable solutions to these learning tasks are precisely the functions that classical computers cannot evaluate. And then that would give you, in principle, a learning task for which there is potential for quantum advantage in learning. Not because a quantum algorithm would be smarter at learning, but because you set up the problem such that it cannot be solved. There are some examples of this. One is like one of, I guess, the more celebrated papers in quantum machine learning theory. The other one I highlight is more recent. It's from Vedran's group and some people at CERN, and it has more of this condensed matter physics flavor. But in both of them, kind of the zoomed out argument is I will set up a learning task such that any algorithm that solves the learning task could solve a computational task. And in this case, it's either computing the discrete logarithm or predicting long-term dynamics of evolving under some Hamiltonian. Because we believe that no efficient classical algorithm can solve the computational task, then it follows that no efficient classical algorithm can solve the learning task. Right? Like this is a somewhat straightforward reduction. Like I would set up I would set up a problem such that the solution is just unattainable by construction, and then I would say that I proved some learning advantage. And yeah, and this is what some papers have been doing, and that's cool. These papers are nice because they connect quantum info with some parts of physics and some parts of applied math, and they give formal guarantees in that like the math is true somehow. But then once you read them, you ask yourself, have, okay, but do I expect to use quantum computers to solve machine learning tasks that have to do with discrete logarithms? Do I imagine that I would want to run these algorithms in practice? Or, I don't know, we still don't know exactly what tasks quantum computers will offer an advantage over, but do we imagine that they will be of this form? And these are questions that you will ask yourself after reading these very formal papers. Now, me personally, what I've been trying to answer is a very related question, but a bit more concrete. And it's precisely, when should we use quantum alternatives to classical machine learning, and what advantages might they offer? So the way I approach this, instead of kind of tackling the whole problem at once and just tomorrow saying, look, this is quantum ChatGPT, it will do everything you want. I like to still formally, but come from like the bottom up, top down. Define some individual properties that I would like to have, and I call this my wish list, and then try to come up with examples that fulfill the wish list. And then in my, like, I have this inner narrative of an iterative process. I come up with a wish list, I try to see if it works. If it does work, then I add an item to the wish list. If it doesn't work, then I go back and think, oh, maybe this didn't work. What can we change? Okay, and for the work I present now, the wish list we started from was, we would like something that is efficient to run on a quantum computer, and we don't pull this thread very long. We just want to do some parameters quantum circuits. We would like something that feels like classical machine learning, and so in this sense, something that's more like, yeah, gradient-based methods or kernel methods, and not some other corners of the literature that are closer to tomography. Yeah, because we're doing all of this for quantum advantage, we would like that it is at least possible to achieve quantum advantage in these problems. And ideally, we would also like to get somewhere where we can solve maybe practically relevant or natural looking problems, at least. This is our wish list, and we'll try to get as many of these items checked as possible. Now, just to give you my view on like our field of quantum machine learning theory, what we all want ultimately is to find good applications, like kind of reasons that justify spending the trillions of dollars that it costs to build a quantum computer. I used to say that we want to find these applications before we have like the fully functioning hardware, but I had to cross this because recently on the news we've had all of these better resource estimates that tell us that maybe early fault tolerance is closer than we thought. Okay, what we want is just to find useful applications. We look around, and what we see is that classical machine learning is doing great. Like, seem to be a good thing to do. So then, yeah, one thing we can do is, can we have something like neural networks, but make it work for quantum computers? And by now, it's a very well-established field that one possible answer to this question is variational quantum machine learning. Variational quantum machine learning is a bit of an umbrella term that has been around for a bit now. And the idea is we will have a quantum circuit that will make some guesses. Will kind of, for the pictures of cats and dogs, it will predict whether things are cats or dogs, and we will initialize this quantum circuit in a more or less random way, so that we don't expect it to be very good from the beginning, but then we'll put it on a hybrid optimization loop where we'll evaluate some loss function, we will ask a classical computer to compute gradients and to make adjustments to the values of the parameters until we eventually have a well-functioning device. And so here, what I think is, okay, a machine learning pipeline involves several steps, like data whitening and post-processing, and then sometimes you do this pruning techniques. What I have in mind for variational quantum machine learning is you take a typical classical machine learning pipeline, you just remove the neural network and put in a parameters quantum circuit inside and keep the rest of the pipeline. And this is the types of situations that I have in mind. And if you ask me specifically what I would like, or what I would say the important question at the moment is for us in like the theory side, would be to find some evidence for quantum advantage in learning, specifically using these parameters quantum circuits, like the variational quantum machine learning models, and I'll explain a bit more about those later. And specifically for practically relevant task. That means with like real world classical data. Anyway, again, I used to say this without hardware. It seems that soon we will have hardware, so then we can start playing around. That's what we want, but what we have so far is part of math, like the part of math that was developed for understanding classical neural networks, and we just applied to these quantum circuits. And then some keywords that are thrown around and that I will mention later in more detail are things like expressivity, trainability, generalization. These are properties not from the quantum info side and not from the quantum algorithm side. These are keywords from the statistical learning theory literature that was developed, among other reasons, for classical neural networks. So what we do is we take a parameters quantum circuit and we pretend it's a neural network of sorts. So we ask it the same questions we would ask to a neural network. To just show a bit the pictures of what I mean, I typically think about classical input, classical output tasks, because then making comparisons between classical and quantum models is a bit easier. So just to name one, we can take the MNIST handwritten digits. We could also take cats and dogs. We look at the input and we say, okay, this is nothing but a very long vector. So somehow I'll take this very long vector of inputs x. I will take another long vector of parameters theta, and I will evaluate some quantum function that depends both on x and theta, and that will make a prediction. And that will be like the label I assign will be just based on this prediction. A quantum function is not a very well-defined term, but what I mean for the purpose of this talk is come up with a quantum circuit that implements a unitary transformation that depends on these parameters. It's unitary on the old zero state, it prepares a parameterized quantum state, and then we just measure the expectation value of some fixed observable for this parameterized quantum state. And that's what we call the function. So this function is real valued in principle if the expectation value and everything is real valued. And the visual picture for this is we have a quantum circuit. I keep things very abstract on purpose. In this quantum circuit, we have some quantum gates organized in layers, and I highlight them in 2 different colors just to point out that I'm not restricting myself in how the information comes into the circuit. So this is a so-called data reuploading circuit where the dark green gates will be dependent on different components of the input x. The light green gates will depend on different components of the parameters, and they are not separated. So we allow the x-dependent parameters and the theta-dependent parameters to alternate. Yeah, and then eventually we reach this parameters quantum state and we fix an observable ahead of time. Now, back to the guiding question that I mentioned earlier and to our wish list for good quantum machine learning models, we see that as I presented this variational quantum machine learning, we check the 2 first directly, because like these quantum circuits, we can set them up to ensure that we can run them and they're not too big. And it's been proposed several times how to perform different machine learning techniques using these quantum circuits. So the thing that we have to show next is that indeed these variational quantum models can solve hard problems, and whether or not they can also solve natural looking problems. And here there's like a very small asterisk that the papers I mentioned earlier that showed proofs of quantum advantage sometimes had more to do with kernel methods and less with gradient-based methods, because we'll be having an emphasis on the gradient-based methods part of the story. Now, the next item on our list is to go around showing that these parameters quantum circuits can actually do useful things. And we find one first obstacle, that because we're demanding that these things look like neural networks have this property that they're a bit messy, and it's hard to make predictions on what they will do before they do it. And the same will be true for parameters quantum circuits. Like we'll deal with non-convex optimization, non-linear functions everywhere. So yeah, it will be difficult in general to just even write down a mathematical formalism for this. And another obstacle that you may be aware of is that there's been already, I don't know, 5 or 6 years of proposals for what to do with this circuit, and several of those proposals seem to be deeply flawed in that it's hard to make them work at scale. And now there's this folklore slogan flying around that there cannot be quantum advantage with trainable parameters quantum circuits. And I'll also say a bit more about this later. Now, this is the end of the motivation / setup. So far, it was a bit vague, but it should be understandable broadly. So if you have any questions now to clarify what I mean, now's a very good time to ask questions. And otherwise, I mean, yeah, as I said, feel free to interrupt me at any point. Okay, so I just gave the zoomed out picture of what's on my mind, what types of things we're looking for, and roughly what we expect to be the problems. But yeah, I work on theory, so I need to be very precise in what I mean. And in particular, when I talk about machine learning, I mean about supervised. I talk about supervised learning with classical inputs and outputs. The mental this is cats and dogs, where a problem is specified by a distribution over inputs x and outputs y. X would be the pictures of like some long vectors, and y would be the labels, which can be either +1 or -1, or cat, dog, or they could also be real value. They could be the price of the Google stock over time or something. And we're trying to somehow find a function that is some form of good fit for this distribution. Instead of doing it directly, what we do is doing it in a supervised way. We assume we can have a few samples from this distribution, meaning we get a few input-output pairs called the training set, and we will try to infer from these training pairs what the underlying patterns would be. And for that, we need to fix a function family, which I call the hypothesis class. This is the set of all possible functions my algorithm could ever output. So you can think of a neural network with a fixed architecture. This is the set of all functions for all possible values of the parameters. Or the same thing with a parameters quantum circuit. You fix where the gates are, and then each value of the parameters gives you a different function, and this is the hypothesis class. And finally, we need the learning algorithm, which kind of steps is outside of the hypothesis class, and it takes as input a training set that was generated from distribution, and it produces as some function in the class. So I write f sub a is a function of the training set, and it's the learning algorithm. Now, in a typical machine learning pipeline for supervised learning, this is what you do. Like in your Python code, in the end, you'll assume you have your training data coming from somewhere. There will be something that happens, and eventually you find a function. If you want to do theory, then you need to define a few more things so that you can start asking questions. The first thing that I will define is the expected risk. It's a quantity that depends on a specific function and on the distribution d. That's why it's r sub d. And it's a measure of quality. In principle, we say that a function is good if it achieves a small value for the expected risk. So generally, small is good. Usually, we assume the distribution d is fixed but unknown, so that we cannot write down the distribution over all possible pictures of cats and dogs, which is a reasonable thing to assume. That means that we can generally not compute the expected risk directly, but somehow our goal is to find a function that achieves a small expected risk. What we can compute directly is the empirical risk, where now it's r hat sub s. This is a proxy for the expected risk, but it's just the measure of quality if we concentrate only on the training set. So like how good we did at fitting the training data. And based on the empirical risk, we can define this function f star, which is a property of the hypothesis family itself, which is given a training set S, what is the best possible empirical risk we can achieve? In principle, we would like this to be close to 0. That would mean that our function family is expressive enough to at least capture the training data. Another question we could ask is, okay, good. This optimal value might be small, but is the value we obtain from the training algorithm also close to it? And this is about how well the training algorithm is able to find a good solution. But finally, we need to remember that the thing we care about is the expected risk, R sub D, and not the training risk by itself, R hat sub S. So we also need to make sure that whatever we found is close to the true value. And with all of these boxes and all these arrows, I can now precisely tell you what use I will make for different words. I will talk about a learning task as the pair distribution expected risk functional. So this is a choice that defines a learning task. I would say a machine learning model is the pair learning algorithm hypothesis family, because together they define what the model does. And then the other keywords are expressivity. Say your model is expressive if it can achieve a small training error. Generalization, which is sometimes called the holy grail of supervised learning, is the difference, or whether your empirical risk matches the expected risk. And finally, trainability, relation between how good you did on the training data versus how good you could have done on the training data ultimately. This is like, if you want to write this down, this becomes a very neat error decomposition that you can define the expected risk of the differences between these three things. And that's pretty neat. And it's kind of my working framework. Does this make sense? Are there any questions?
A small question. In this
Yes,
moment, trainability and generalization in this picture are some way unrelated, right? You can.
Yes. Sorry, my goal now was to decouple the three sources of error entirely. So they are completely unrelated.
Okay.
Yeah. And that was my goal. I should have said this from the beginning. Yeah, exactly. I would like to talk about whether a model is good at solving a task. And to do this and to be able to compare different models, it's good to separate different sources of error.
Thanks.
Pleasure. Any other questions? This is a bit.
Yeah, sorry. When you say separate, you mean literally you rewrite some of these factors somehow, or just conceptual separation?
Well, both. I like it conceptually, but if you write it down, okay, I didn't write it down, but if we try it together, okay, all these approximate symbols, we can replace them by the absolute value of the difference between those terms, and this will be the absolute value of itself. Then RD, okay, and we assume that RD is positive, and that the training error is smaller than the true error, which are reasonable assumptions. Then RD is equal to this difference plus this difference plus this. And you can see that this will cancel with this will cancel with this. So this other combination is exact.
Okay, yeah, makes sense.
Yep.
Additively.
Yeah, this is something that I haven't managed to use for paper so much, but I like it very much. Okay.
Thanks.
Yep, pleasure. Okay, now is about whether a model can solve a task or not, but if we want a quantum advantage, we'll need to compare different models. And so very briefly, I define and the training set the same as before. Now I say my quantum machine learning model will be one where the hypothesis family is a family of quantum functions. And a machine learning model is one where both the training algorithm, the learning algorithm, and the hypothesis family are classically efficient functions. But in principle, because I keep the inputs and outputs classical, I can give the same training set to both models, and they will produce two functions that I can compare directly. And here, notice the difference is that FC is an element of uppercase FC, and that the training algorithm now the learning algorithm, I call it classical. Now, once we do this, the reasonable metric to compare these outputs would be the expected risk of the task that we're trying to solve. So we will compare whether the quantum model achieves a much better expected risk than the classical model. And we'll say if this happens, we have quantum advantage. It's a bit messy. To talk about quantum advantage in learning, we need to talk about the expected risk, but the expected risk is not the thing we optimize directly, but rather it's the empirical risk. So there are many things that could go wrong in many ways. But still, this is the clean definition of what our goal should be. And then there's this very famous concept. Oh, sorry, is this clear? Otherwise, yeah, we can feel free to ask. Okay, now one concept that we're familiar with, which is Barren plateau. Barren plateau equals all the bad things in hell. So if you have barren plateaus, you did something very wrong. But what happened? What can we do? But barren plateau is a concept that's usually defined for, I would say, the variational quantum eigensolver problems. So for quantum optimization problems, where the only goal is to find an optimal solution to an objective function, and that doesn't necessarily come up in the richer supervised learning framework. So very briefly, let me present to you 4 different possible function families, hypothesis families. These are independent of the learning algorithm, but just so that we can talk about them. We call them F1, F2, F3, and F4. A quick glance tells us that they are kind of different. And now just to give names to these things, I would say that F1 and F2 concentrate with respect to theta. Sorry, I should have said. To simplify things, I said that X is one-dimensional. And then what I did is take 3 different values of the plot the function X to f of X for those different thetas. So different thetas are different lines, and for every line, it's a function from X. What we see on the top row is that all different thetas, they don't produce exactly the same function. So we will say that these functions concentrate, and we'll say that they concentrate with respect to theta. Different still give different values, but different thetas give roughly the same function. Now that I said it this way, maybe you can see that on the first column, we have a similar behavior, but with respect to X. We see that maybe different thetas can give similar or different functions, but the value of the function for all X is essentially the same, or it's very close. We will say that these function families concentrate with respect to X. Now, if you come up with a very nice quantum machine learning model, and I look at the hypothesis family, and I find that you suffer from this property, that you concentrate with respect to theta or with respect to X, then it's clear that you will have some problems in using this as a quantum machine learning model. In particular, we'll say, and this is what a barren plateau is, we'll say a barren plateau is a property of a function family where you have concentration with respect to theta. And it should be clear that it's at least bad for gradient-based. Because in gradient, like when we do gradient descent, what we do is we take some value of the parameters that gives us some value for the expected, for the empirical risk. And then we explore the area around the parameters we started from, and then we try to pick a good one. If it happens that most parameters give rise to the exact same function, then the gradient will be 0 everywhere. And yeah, your gradient-based training algorithm will not be able to do much. But yeah, okay. Concentration seems to be a bad property in general, but to be precise, when we talk about supervised learning, we'll say that the equivalent of a barren plateau is when you have concentration with respect to the parameters. Okay. And yeah, there's this funny thing if you're on the case of F1, which is where you have concentration with respect to both theta and X. F1 shows very clearly that this will not lead to quantum advantage, because even if you're using super big quantum circuits that are super non-simulable, there's a cheap way to dequantize or to provide a classical algorithm that performs similarly, which is just output 0. And then with high probability, you succeed, which is a fun thing, that such a silly algorithm can dequantize other things. Okay. There's this also well-known paper that kind of relates barren plateaus with the possibility of classical simulation. in the language of supervised learning and the language that I've introduced here, the keywords we use should not be Barham plateaus and simulability, but rather quantum advantage and trainability. And this paper raises the alarm that it could be that all quantum models for which we don't have Barham plateaus are classically simulable, and that should be a problem. So what do we do? And yeah, just to connect back to classical machine learning, there had been similar problems to Barham plateaus in classical machine learning that went under the name of vanishing gradients. And yeah, one question is whether similar solutions to the ones that resolve the vanishing gradients problem could also resolve the Barham plateau problem. And as far as I know, this is an active field of research. Now,
Sorry,
like to,
a small question in the previous slide.
Yeah.
So for F1, where you have concentration in both x and theta, you have the quantization, so classical algorithm. But what about, for instance, F2 and F3? You can say something on these two cases, or?
Yeah, then it's not so clear. So it's clear that that's a bad machine learning model. This we agree. It's not so clear that you could dequantize it in the same straightforward way, because even though these functions are constant, it could be that the precise value they take depends not trivially on the thetas, in which case kind of it's a constant function, but you don't know which constant function it is, so you cannot say, like you would not be able to predict these values classically. But if you're trying to solve a learning task where the solution is not a constant function, then in principle, whatever classical machine learning method that you in principle will be better than this one. So it should be easy to dequantize. Just it's less immediately straightforward. And similar to F2, what F2 says is that even though you tell yourself that you have in practice you have mostly one function, because different values of theta give you the same thing, then, well, it could be that the function you have is exactly the function that perfectly solves the problem, in which case there could still be room for quantum advantage. It's a bit of a contrived situation, maybe, so it's up to you to see if that satisfies you or not. But yeah, so there are, one can say that it's easy to think of situations where using F2 or F3 could still be dequantized, but then it's a bit more nuanced, that like you need to think that it could go both ways, I guess. But it's clear that F1, whatever you do, you can also do classically.
Like F2, if you imagine a standard quantum algorithm where there's no parameters,
yeah, exactly.
then you have it's kind of like F2, no? There's no theta to vary, but you still have presumably quantum advantage if the quantum algorithm.
So imagine F2 is the factoring function and the learning task is there, then you will have quantum advantage, exactly.
Okay. Whereas F3, the way I understand it, you're saying that from the output of the algorithm, you essentially cannot retrieve X, right? So there is no possible information.
Exactly.
Okay.
Exactly. And so exactly. So if you picked a theta and you run the quantum algorithm, then once you run it once, you know what the value will be always, but it could still be hard to predict the first time you run it.
Right. Yeah.
But yeah, it's a bad quantum machine learning model still, because it's just a constant function.
Mm-hmm.
Yeah. Okay. Sorry. Like this was more for illustrative purposes, but yeah, just to have the mental picture that it's a bit different to think about concentration in supervised learning than to think about concentration in VQE or the ground state energy problem. Okay. Then I will briefly talk about this one work that we did with and yeah, just to give them. In this work, we managed to show that using this variational quantum machine learning model, messy ones with gradients and everything, we could also prove that you can solve hard problems. What we did not manage to do, which made me a bit sad, was we did not manage to prove beyond that it could also work for non-contrived problems. And so we have this Venn diagram. I hope it's not too small, but like we have these 4 properties that we would like. The names are kind of different, like the ones on the right are a bit more technical, but it's clear that the ultimate goal we want is to find machine learning models that fulfill all 4 properties. We have as examples that neural network fulfill 3 of them. Some previous works on proving quantum advantages in learning fulfill 2 of them. We managed to fulfill 3 of them. And the next steps should clearly be to do all of them. But this is just a spoiler. Let me tell you how it works. Again, we need to be the people in the room. So we had to define everything very carefully because we noticed that this had not been done for supervised learning with quantum machine learning models. Trainability we already defined. Barren plateaus we already defined also. Before I talked about concentration, but this is the same as saying the variance is essentially 0. Dequantization we also defined kind of, because dequantization of quantum advantage. We defined quantum advantage when the expected error of the quantum algorithm was much smaller than that of the classical algorithm. So if it's bigger or similar, we will say that the model has been dequantized. And this is, this definition of dequantization, hopefully you will agree with me that it's a reasonable one as I presented it, but just be aware that it's not the one that usually you see on the news, because this is specifically dequantization for a learning task, not just simulation. Where classical simulation of a function family is a property that is the one you see in the news, which is you say you have a family of quantum functions. Well, what if I come up with a classical algorithm that can produce the same input-output relations as those quantum functions? Well, then I'm classically simulating your function family. And in this work, what we did is define all of these things very carefully and then kind of ask questions. Does this imply that? Can you have both of them simultaneously or not? And for this, we define or try to define carefully what it means to be a variational quantum machine learning model, because we know that there are there are older quantum machine learning models based on quantum kernel methods that already prove that they can solve hard problems. So we had to add extra assumptions or come up with a definition that would capture the essence of what people mean when they talk about quantum machine learning in practice. And this was a bit difficult because we also realized that this had not been done before. No one had been pedantic in this particular question. So we say a quantum machine learning model is variational if the parameters that you fit appear inside the circuit and not just in the classical post-processing, which is the case of quantum kernel methods. The learning algorithm that fixes the correct parameters must be gradient-based, which is much messier than other alternatives. And then we wanted this idea of modularity from neural networks. So we'll say that you need to fix a layer template, and then the only thing you're allowed to do is repeat it and arrange it how you like. But here the goal was to prevent that we can just compile Shor's algorithm in a weird way and then pretend that it's variational, but in the end we're just doing the Shor thing again. Now, then we had, we were very inspired in this paper. We had another small joke. So here we paint the spectrum of quantum machine learning models, variationalness, and we have on the left the kernel methods that were used to prove quantum advantage a long time ago, which are distinctly non-variational. And on the right, we have the things that they discuss in this paper by Marcos Ceres and the people in Los Alamos, where they have things that are very variational, but are also dequantizable in that they are similar. Then the definition we give is a bit more than non-variational. We would like to give a good definition of very variational, but noticing that we were the first people to try to do this, maybe there's some improvements that we didn't think of. So we leave open the title of very variational to be fixed in time once more people think about it. And for now, we call these things variational, which is funny because if you say it quickly, you cannot really distinguish the two. So then our goal will be to say whether there exist variational quantum machine learning models that can provide quantum advantage. And this was the main result of this paper. Indeed, there exist variational quantum machine learning models, which are gradient-based trainable and non-dequantizable, aka they give quantum advantage. And yeah, okay, it was very quickly. The trick for the proof is to combine a function or a circuit that you will not train, but which evaluates a function that is hard to learn and hard to compute, put together with a small quantum circuit that is fully simulable if necessary, that you will train. And if you put them together, this gives you the right tools so that you can set up a learning task, which uses the trick of the solution will be hard to evaluate, so classical algorithms will not be able to do it. And yeah, so like this proof just allows us to confirm that for at least this family of variational quantum machine learning models, it is not true that trainability implies dequantization. We prove that there are models that are trainable and non-dequantizable at the same time. And then, I mean, yeah, the way we build this circuit is a bit different from the way you would usually build your quantum machine learning models. Still, this thing is very contrived, so it's not the ultimate solution, but we thought that maybe it can be used as a source of ideas for new designs for quantum machine learning models. Then, now that we have the pedantic hat on, we went back and really cleared fully the landscape of all of these properties and whether they imply each other or not. And we unified the language. I found some interesting, maybe counterintuitive situations that, like, for example, trainability and barren plateaus are formally like completely independent conditions. That was fun. But yeah, so the main message is that we managed to show that you can have trainable and non-dequantizable variational quantum machine learning models. Are there questions about this? I kept it deliberately non-technical on purpose. But, yeah.
Maybe can you clarify the difference you mentioned before about the two different ways to understand dequantizable? Like you said, there is a difference between dequantizable for a parametric family of functions and the supervised context. Like
so, yeah, so I zoomed out answer, and then we can see if we need to specialize it more. So we use quantum computers for specific tasks, and usually this task comes with a nice metric that assesses whether you solve the task or not. Our observation was that the tasks that we, like the learning tasks, are of this type. There's just like a well-defined problem, and it has a well-defined quality of solution metric. This is also true for computational tasks like factoring. You can ask yourself, well, were these things factors, yes or no? And also for like the ground state energy problem, like you can you'll try to get the lowest possible energy you can find, and then there are some bounds, and you can assess whether you're good in getting the solution. What we wanted to come to say is we need a notion of dequantization that's specific to the task we're trying to solve. And what I wanted to say is that the notion of the quantization that we use is a bit different from the notion of the quantization from, let's say, the ground state energy problem. So let's say I have a quantum circuit and I use the ground state of some small molecule. When people say this, they either mean that they can fully simulate the circuit step by step, or that there's a different method that does not simulate the circuit, but which achieves better energy, say, like lower energy. Mm-hmm. What we give is a notion of the quantization that is morally equivalent to the second one of these, where you don't demand that you are able to simulate the model, but rather that you'll achieve similar or better performance on the task you're trying.
So like you don't ask to be able to simulate the circuit that solves the problem in the quantum case, but you can maybe find another algorithm that is completely classical that solves the same problem. Okay.
Exactly. And this is here. We also do it the other way. So there are quantum circuits, or there are learning tasks and which are dequantizable, but which are not necessarily simulable.
Right.
And like if you use a very, very big model, a very, very big algorithm that being okay, where the data. Okay, so I don't know how to say this in a very concise way, but there are some papers that study effect of encoding of classical data into quantum circuits, and they realized that even if you invest a lot of quantum resources on your full circuit, if the way you encode the data is not smart, then you end up evaluating very simple functions. Right. And if you're if you're solving a task where simple functions are good enough, then it means that your task was simple. And so a classical machine learning model could solve the task, even if they could not simulate your circuit because you invested a lot of quantum resources, just you did not invest them in the right way. So that in the end, I don't know, maybe the function you're evaluating is a small trigonometric function, but you will not be able to predict what the values of the coefficients are, or things like this.
Yeah. So you mean cases with exponential concentration you're talking about, yeah. Essentially. Yeah.
Not even, but maybe we can talk about this. But like the exponential concentration, the way your x comes in can make a big difference. Because imagine you have 17 million qubits, put your x only once on the first qubit with a Pauli Y rotation, then you measure whatever, it doesn't matter. Then you know that the output function you'll be evaluating will be of the form a0 plus a1 times cosine of x plus a2 times sine of x. And so it will be like there's those three free parameters will depend on your entire circuit, and it will be like, and if you were able to simulate the circuit, then you would be able to say what those three parameters are. But those three parameters could easily encode Shor's algorithm. Like it could be that the value of a0 is the solution to some factoring task. So you cannot say what a0, a1, and a2 are. But so in this sense, the function is notable. But if now you evaluate this function in a few points, then you can learn those parameters from data. And the function is easy enough or simple enough that you'll be able to dequantize the learning task, even if you're not able to simulate the function.
Yeah, makes sense.
Yeah, but it gets a bit subtle very quickly. But yeah, I mean, that's the idea.
Yes. Okay, one arrow is clear. The model that can be dequantized but cannot be simulated. Mm-hmm. But the way around, the one that can be simulated but not dequantized, it seems counterintuitive. I mean, if I simulate,
it is counterintuitive. This comes a bit in the next slide, but if we allow the learning algorithm to be a quantum circuit, then even if the hypothesis family is simulable, you can still find quantum advantage because the learning algorithm could be doing quantum. So this is why there are two arrows here. The blue arrow says, well, if the training algorithm is limited to be a classical efficient training algorithm, you're right. If you can simulate, then you can literally do everything the quantum algorithm is doing. But yeah, there are some edge cases where using a quantum training algorithm, you can achieve quantum advantage.
So here simulation doesn't mean efficient simulation. It means
it means efficient simulation.
Okay.
But notice there was the hypothesis family and the learning algorithm. Those were different things.
Okay.
And here, when I say simulation, I mean it in this sense, which is simulation of the hypothesis family only. And if we look here on the classical model, I demand that the training algorithm is classical. But on the QML model, I didn't demand that the training algorithm is classical. So it could be that even though F is a classical function family, that A still does funky quantum things. But this is a bit of an edge case. I would not worry so much about it. Like there's a nice proof in some paper, but yeah, it's not something that will show up in practice very often, I think. Yeah, but yeah, okay. But here we were being Mr. Pedantic, so we had to make sure we covered all the corners.
I mean, while we are here, can you also say something about, you mentioned you can have trainability in the presence of parent plateaus before, right?
Oh yeah, okay. This is also a bit funky.
This is still in the context of parameterized circuits, I guess.
Well, it's in the context of parameterized circuits, but because I'm not demanding gradient-based trainability, but it's just trainability, then imagine you have a trainable model that is trainable for some reason. Then you can recompile it as a large model with more parameters flying everywhere, where you will have a barren plateau on this larger model with more parameters. But because you compiled it yourself, you know how to carefully pick the parameters such that you recover the trainable model, so that you can you can artificially add barren plateaus to whatever you have.
Right. It's non-gradient based trainable
yes.
trainability. So if you have discrete stuff, maybe or something.
And indeed, if you are gradient based trainable, then it follows that you don't have a barren plateau.
Okay, that makes sense.
Yeah. Mm-hmm. Okay. I'll try to be a bit quicker on. Or okay, you can tell me once the time is up. But in this previous, we were similar. Like in this work I just mentioned, we were similar to the work I mentioned at the beginning, in that the source of quantum advantage that we use is rooted on like gravitational speedup. So just because we can compute these functions quantumly and not classically, it follows that there is quantum advantage. Then on these papers, they have this discussion on places where even if you have a classical model, you can have quantum advantage if the learning algorithm is quantum. So this is very nice because it's clear that the source of the quantum algorithm is not to produce better like functions that could not have been found otherwise, that could not be evaluated classically, but rather it's just better at navigating the landscape of solutions. And then a third possibility that is closer to these tasks from classical shadows and quantum assisted classical machine learning would also be to provide higher value training data. And on the, I wanted to briefly mention a second work, which ties very nicely because it tries to, we try to argue that all of these questions of trainability and of dequantization and simulation and quantum advantage, it's very nice to look at them from the point of view of function families, instead of worrying about quantum circuits and entanglement and magic and things that in the end are not, don't directly show up in the machine learning task you're trying to solve. And we'll get back to this picture later, but you see that you will have quantum circuits, they will relate to function families, and some keywords that have already appeared, like this concept of classical simulation. It also relates to classical surrogates that are also quite trendy and potential for quantum advantage. And okay, this is the one ugly slide I added, but just to be precise in the language, say a parameterized quantum circuit is specified by an input state, some parameterized unitary, and an observable, fixed observable that we measure at the end. And from these ingredients, we can define a function, which before I called a quantum function. For machine learning, we need these hypothesis families, which is a function family. And so parameterized quantum circuits very nicely give rise to these sets of functions in which you fix the architecture and you consider different function for every choice of the parameters, and then the whole set is the function family capital F. Now, if you put some training algorithm on top that will fix the values of the thetas, you have a quantum machine learning model. And there's this view, sometimes referred to as the Fourier picture of parameterized quantum circuits, that says that very often these functions, the functions that are exactly of this form, can be written as some linear combination of some other function basis. Very often, okay, and here k is the index of the function basis. K could well be a multi-index, so this is just for simplicity. Usually these tks are these trigonometric functions. But yeah, notice that we have the input x, some function basis t, the parameters theta, and some coefficients c. That means in the Fourier picture of parameters quantum circuit, it's very nice because the role of x and the role of theta gets separated very nicely into a function basis and a set of coefficients. Now, let's say we have a parameters quantum circuit for which we know what this description is. So essentially, we know what the function basis is. It could still be that the map from theta to the parameters is difficult, but at least we know that the function is of this form. Once we know this, we could define a related function family, f prime, where we just consider all possible linear combinations in this basis, where now we free the parameters entirely. Like now this capital C does not depend on theta, we just free parameters themselves. And we see that if we have a parameters quantum circuit, which defines a function family, from which we know what this function basis is, then this immediately defines f prime immediately. So we haven't done any tricks or any arbitrary choices here. If we followed along, be clear that all functions in f are also in f prime, because whatever the choice of theta is, it will produce some value of the parameters, and that is exactly how we defined f prime. It's all possible values of the parameters. And this is maybe not so surprising, maybe it's a bit surprising, but there's a funny situation, paradox, that it could well be, and it's the case in many situations, that even though the function family f is smaller than the function family f prime, it's contained in it, evaluating functions in f is hard, whereas evaluating functions in f prime is easy. And here the trick and the key is the theta dependence of the coefficients. Just because we know that the function is of this form, it doesn't mean we know the exact value of the function, because the map from theta to ck of theta could be weird. But in the second function family, in f prime, well, we pretend that we have a list of parameters ck. So if you just give me the parameters, I can evaluate the function directly. Like there's nothing that can go wrong. And yeah, it's a bit weird that the bigger function family is somehow easier in this sense. Does that make sense?
Ask you here?
Yes, please.
So when you say f classically hard, what do you mean exactly? Because you don't mean I pick any f theta from f, and that will be classically hard.
No, I mean there exist some thetas for which it will be hard. Yes.
Okay.
There some thetas and some x's.
Okay, and the same for f prime.
Yeah, I mean, okay. I guess I should also explicitly say that f prime is classically easy if the number of terms in the sum is not too large. But yeah, but then f prime is easy because if you tell me the parameters and you tell me x, then you told me everything there was. So I can just evaluate it.
And so, because for f, you're saying, okay, there is a value of theta such that the corresponding f theta is hard to simulate, or you're saying that it's hard to find the theta?
Well, those are the things. If you could find the, sorry, I'm saying from a given value of theta, it will be hard to evaluate f theta of x, and in particular, it will be hard to find the coefficients for that value of theta.
Okay, so the difference then is the way you specify the functions, right? Okay,
exactly.
In one case
100%.
you specify it through theta, and the other case, okay.
I just listed, yes.
Another question, so this function basis representation, this separability, you mentioned it's trigonometric function, but that's structure is specific of some kind of circuits, right? Like there is not, like, is this general, like you can always separate things this way?
It's
or specific for?
It's quite general, yes. Yeah, what ends up happening is that both the lowercase c coefficients and the t functions, they are both trigonometric in some way. And but yeah, you can.
But these assume specific encodings, right? If I remember correctly, like that you could x to exponent.
This assumes the easy encodings. Yeah, that's why I say, like, that's why I wrote it in general as t of x and not specifically as the trigonometric ones. And yeah, I mean, there would be, you could deliberately break this picture. That could
you would break the trigonometric. Okay, the trigonometric assumes encoding of that kind. So if you do it in general, there is always a TK of x, you're saying? Or
I'm saying that there are situations where you could break the nice picture that the function, like a function basis, yes, separability.
Okay. Okay.